So my name is Dr. Keshavulu, Associate Professor, Department of Physics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss about the laserless spectroscopy. Last session we discussed about the previous session we discussed on the introduction of laser, brief history of laser, evaluation of practical lasers, characteristics of lasers, spontaneous and stimulated emission, these types of lasers and its construction and working principles, its applications of lasers. These are topics last session we discussed on these kind of topics. Today we are going to discuss about the continuation with the last session. So objectives and the scopes of research. First one is spectroscopy and its properties. Next, electromagnetic spectrum, motivation and lanthanide or rare earth ions. Lanthanide and rare earth both are similar only, that is black elements. That is a motivation of lanthanide and rare earth ions. Next, definition of glass, importance of glasses, basic properties of glasses and advantage of glasses. These topics we are going to discuss about in this objectives and scope of research in today's topic. So first one is objectives and scope of research. In my research topic, main objectives and research scope of research is mainly spectroscopy. What is meant by spectroscopy? Before knowing the spectroscopy is one of the pioneering branches in science that deals with understanding the physics and chemistry of materials for the development of devices through systematic study of the radiation, that is radiations through observed or reflected, emitted or scattered by a material. These are the very important thing for the spectroscopy. In spectroscopy, we develop the device through systematic study of the radiation through absorbance, reflectance, emission or scattering. These are we are going to study in the spectroscopy properties. Although strictly speaking of them, radiation only deals with photons. Radiation is nothing but a photons. Photons is nothing but a small packet of energy that is comes from the electromagnetic radiation. Spectroscopy also involves in the interaction of other types of particles such as neutrons, electrons, protons, which are used in the investigate matter. Moreover, the optical spectroscopy provides an excellent tool to obtain information about the electronic structure of the absorbing emitting centers, that is atoms, ions, molecules, defects, etc. Their lattice location and their environments. These are mainly involved in the optical spectroscopy. Optical is nothing but a light. So light spectroscopy, we can discuss about the electronic structures, how electronic structures looks like, that is absorbance, emitting centers that is mainly based on the atoms, ions, molecules, defects. These are we are going to discuss about in the optical spectroscopy. In other words, optical spectroscopy allows us to look inside of the solids by analyzing the interacted electromagnetic radiation. So these are the mainly interacted with the electromagnetic radiation. So electromagnetic radiation is mainly from the electromagnetic spectrum. So we are going to discuss in the electromagnetic spectrum. So here in electromagnetic spectrum, there are different kind of wavelength ranges. There's different types of energies. This starting from, this is a radiation type from radio waves, microwaves, infrared waves, visible waves, ultraviolet, X-rays, next gamma rays. These are the different kind of energies in the electromagnetic spectrum. So starting from the radio waves energy will be very high. At the same time, energy will be low. Wavelength will be more, means energy will be less. This is the main thing, main concept here. So radio waves, microwaves, infrared, visible region. Here in this region only, in our human being, in naked eyes, we can see this visible region only. That is that wavelength range from 350 nanometer to 750 nanometers. These are the visible range. So human naked eyes, we can be able to see this kind of region only, visible region only. So that is comes from the fluorescence bulbs. This is fluorescence. In this region only we can see the visible range. Next, ultraviolet. This is more energy. Next, X-rays. Next, gamma rays. These are the different kind of energies in the electromagnetic spectrum. If you see, the first is wavelength, and here last is energy. See here, wavelength. Starting from wavelength in meters, 10 cube to 10 power minus 12. So energy will be wavelength energy. That means 10 cube to 10 power minus 12 range order. Here energy 10 power minus 9 to 10 power 6. Okay, these are the different kind of energies. That means wavelength and energy, main based on the electromagnetic spectrum. So this is AM radios, microwave ovens, radars, hormones, fluorescence bulbs, X-rays, and radioactive elements. These are involved in the electromagnetic spectrum. These are the electromagnetic spectrum. This covers the all kind of energies. That's from radio waves to gamma rays. In between, there is a infrared and visible ultraviolet. These regions we are studying the mainly for in the glass materials. We can able to study the visible range and infrared and for infrared and ultraviolet. These regions we are going to study in the different kind of laser glass spectroscopy. These are we are going to discuss about the next slide. What is the motivation of lanthanide ions? The spectroscopy technique determines the identify the structure, the environment of the atoms and molecules by the analysis of the radiation emitted and observed by them. Therefore, the spectroscopy is not only limited to physicists and chemists, but also span over almost all the fields. So, not only this motivation of the lanthanide ions, not only limited to the physicists and chemists, it also mainly almost all fields of applications are useful. That is biology, communications, geology, astronomy, defense, industrial, medicine, forensic, and so on. So different kind of applications whenever the solid material is doped with lanthanide ions, lanthanide or rare earth ions. So these applications are very huge. That is, we can biology also we can applicable, communication system, geology, astronomy, defense, industrial, medicine, forensics. Also, we can use the different kind of laser glass spectroscopy whenever doped with lanthanide ions. In recent years, spectroscopy studies of trivalent lanthanide. That means trivalent lanthanide means valency is 3 plus lanthanum ion. Ln 3 plus ions based materials are attracting much attention due to their potential technological applications in optical devices such as solid state lasers. So, ruby laser is one of the solid state laser and the neodymium doped YAG laser. That means here rare earth ion, that is lanthanide ion. That means neodymium is the one of the lanthanide ions. Doped with YAG, yttrium, aluminum, garnet, host material. We are doped with that solid material is doped with lanthanide ions. Here the example we are taken is neodymium ion. So that is one of the example in the solid state lasers. So ruby laser and ruby is doped with chromium 3 plus ions. Okay, transition metal. That is solid state laser. Ruby is one of the first solid state laser is chromium doped with aluminum oxide. That is ruby laser. Other one is neodymium doped with YAG laser. These are the different kind of solid state lasers. Next, light converters, optical fiber amplifiers. We can lanthanide doped with glass material. We can draw the optical fibers also. So that is used for the optical fiber amplifiers. For telecommunication applications, we can use the optical fiber amplifiers. Next, optical storage and data storage purpose also we can use the lanthanide doped glass materials. Next, phosphors and sensors, planar waveguides, and so on. These are the different technological applications whenever glass material or solid material doped with lanthanide ions. These are the main motivation of the laser glass spectroscopy. Next, coming to the rare earth ion table. This is the different kind of lanthanide or rare earth ion elements in the periodic table in F black elements. That means F black elements among the 15 elements from atomic number 57 to 71. These are the atomic numbers from starting from lanthanum La. That is Latin name is lanthanum La. Next, cerium. That is atomic number 57, 58. Next, prismodium Pr. That is atomic number is 59. Next, neodymium Nd. This is the atomic number 60. Next, promethium Pm 61. Next, samarium Sm 62. Next, europium is 63. Next, gadolinium Gd is atomic number is 64. Next, terbium is 65. Next, dysprosium Dy 66. Holmium Ho. So 67 atomic number. Next, erbium Er atomic number 68. Next, thulium Tm atomic number is 69. Next, yttrium Yb 70. The lutetium is 71. So actually 14 elements mainly belongs to the lanthanide and last one is a 15 element is lutetium. Sometimes it acts as a lanthanide and also some metal properties. This is lutetium. So among these 14 elements, we can dope with the glass materials. We can study the different kind of laser glasses by doped with lanthanum, cerium, prismodium, neodymium, promethium, samarium. These are the 14 elements of the F black elements, that is the lanthanide ions or rare earth ions. By using this rare earth ions or lanthanide ions, we can develop the different kind of laser classes. Next, what is the electronic configuration? This is xenon. Xenon is atomic number is 54. In helium, neon, argon, krypton, xenon. Xenon atomic number is 54. This is electronic configuration from xenon is 54. Next, 2 plus 1, 3. So 54 plus 3, 57. So this is electronic configuration of the lanthanum ion. Lanthanum atom number is 57. That electronic configuration, neutral atom electronic configuration, not trivalent. Neutral means 0. That means normal lanthanum atomic number is 57. That electronic configuration is this one. Next, observe valency state. This is valency state of the lanthanum having the 3 only. Only one state, that is 3. 3 level. 3 atoms will be valency state, that is 3 atoms. 3 valency. Next, cerium is having the xenon 4f2 6s2. This is having the 2 states, 3 level state and 4 level state. That is the observed valency states, 3 level or 4 level states. Next, if you see the neodymium, xenon 4f2 6s2. This also having the 2 states, 2 and 3. This is next here. This is the trivalent atom electronic configuration. This is a neutral atom electronic configuration. This is trivalent atom electronic configuration. Xenon is 4f0 because 3 plus state. Lanthanum 3 plus. So 5d1 6s2. The 3 level will be valence state. That is last. Valence is nothing but a outermost orbital electrons. That means 4f0 only. That means 5d1 6s2 will be 3 plus state. No, that is why it will be removed. So 4f0 only. Xenon 4f0. That is ground state level. We can say the ground state level. We can write the 2s plus 1 Lj. By using this formula, we can calculate the ground state of the lanthanide ions or rare earth ions. See here, 2 plus 1 is the spin multiplicity. L is the total orbital angular momentum. J is the total angular momentum. Total angular momentum. By using this formula, by using 2s plus 1 Lj, by using this formula, we can calculate the ground state of the different lanthanide ions. So first lanthanum ion ground state is 1s0. So spin multiplicity of the lanthanum is 1. S is the total orbital angular momentum. That is S. Next, J is the total angular momentum. That is 0. In the case of lanthanum ions, its value is 0. That is why ground state of the lanthanum 3 plus ion is 1s0. This lanthanum 3 plus ion, trivalent lanthanum ions, so 1s0. In the case of, you see the neodymium Nd, is the xenon 4f3. So electronic configuration 4f3. So that is ground state of the 4I 9 by 2. This is the, by using of this formula, we can calculate the ground state of the rare earth ions or lanthanide ions. These are the different lanthanide ions, trivalent ions electronic configuration at the same way ground state level. So ground state, each and every atom they are calculated by using the formula of 2s plus 1 Lj. Here see 2s plus 1, S is the spin. So 2s plus 1 total complete spin multiplicity. L is called total orbital angular momentum. J is the total angular momentum. By using this formula, we can calculate the ground state of the each and every lanthanide ions. In this table shows the mainly electronic configuration of the neutral atom electronic configuration. At the same way, what is the valency states? 3 level state or 4 level states or 2 level state. These are the valency states. At the same time, trivalent ion electronic configuration, ground state of the lanthanide ions. In this table shows the huge data. What kind of lanthanide ions in the F black orbital. Next, what is the atomic numbers? What is the neutral electronic configuration? What is the valency states? What is the trivalent rare earth ion of the electronic configuration? What is the ground state of the each and every lanthanide ions from lanthanum to deuterium? So these are the important. So by using this 14 lanthanide ions or rare earth ions used to, we can develop the different kind of laser classes. So again, what is the main motivation of the lanthanide ions? So lanthanide ions belongs to the 4f orbital. 4fn electrons shielded by 5s and 5p electrons. So each and every lanthanide ions will be shielded by the, shielded means it will be surrounded by the 5s and 5p electrons. So if you see the outermost electronic state, we can see the 5s and 5p electrons. Now similarly pattern is in all materials. So that similar pattern, because each and every lanthanide ions belongs to the 4f orbital only, 4f orbital. So similar pattern we can observe in the all the lanthanide ions from lanthanum to deuterium. Next, several excited state suitable for the optical pumping. So each and every lanthanum ions having the different kind of excited state. Each and every individual lanthanum ions having the different kind of energy levels, the excited states. So lanthanum ground state to different kind of excited state levels. So that is why several excited states suitable for the optical pumping. Next, emit narrow line. So each and every lanthanum ions will be emit the narrow beam of the light. Monochromatic light means it exhibits the single wavelength. That's a monochromatic means single wavelength of the light will be emitted by using the different kind of lanthanum ions. And have long emission lifetime. Each and every rare earth ion doped with the solid material is having a different kind of lifetimes. That means decay times, the emission times. Whenever pumping with the different energies, we can get the different kind of emission lifetimes. So each and every lanthanide doped ion having the different kind of lifetimes. That also having the longer lifetime. That means in milliseconds, the order of the lifetime will be milliseconds or microseconds or nanoseconds. Or most of the lanthanide ions having the milliseconds of the range of the lifetimes of emission lifetimes. This last one is luminescence in all spectral ranges. So we can get the luminescence in the all spectral ranges means we can see the infrared or far infrared, visible, ultraviolet. This kind of range we can cover with the different kind of rare earth ions. So we can, most of the rare earth and visible rare earth ions is dysprosium, prismodium, samarium, europium. These are comes under the visible region. Just if you see the ytterbium, YB, these are infrared and mid-infrared range also we can cover the different kind of lanthanide. That is why luminescence in all spectral ranges. We can cover the different kind of lanthanide ions. We can cover all the spectral ranges. Last session we discussed that is electromagnetic spectrum. So we can cover the spectral ranges, the luminescence in all spectral ranges. So ideal for lasers, photonic and phosphorus application. That means these are the different kind of applications by using the lanthanide ions. Solid state lasers you already discussed. Optical fiber amplifiers applications. Next, optical storage materials, light converters, sensors, phosphorus, acousto-optic modulators, planar waveguides, and etc. This kind of applications we can develop by using the lanthanide ions whenever doped with glass material. So therefore, ideal for lasers, photonic and phosphorus applications. This is the important active ion is the lanthanide ions. So from lanthanum to lutetium, we can use the different kind of laser applications. Next, coming to the recently research and spectroscopy of lanthanide 3+ doped glasses is increasing day by day in order to achieve improved optical quality materials besides cost effective. This is a very important thing. Now the research and spectroscopy in lanthanide doped glasses increasing day by day in order to achieve improved optical quality. Optical quality means light quality will be very, very important. Quality of optical quality, laser quality of material we can develop. At the same time, economically cheap, it is cost effective. That is very important. Whenever solid material doped with lanthanide ions, we can achieve the optical quality materials at the same time economically cheap, cost effectiveness. This is because of their interest and potential applications as a laser, photonic, waveguides, luminescent device applications we can use for the lanthanide ions. It is observed that though the absorption and emission band position of these ions are not very sensitive to their environment, the radiative and non-radiative transition probabilities change with the host material. So here we can observe one thing, this radiative and non-radiative transition probabilities changes with the host material. Whenever the lanthanide ions doped with a different kind of host material means we can tellurate, borate, silicate, different kind of host materials. Whenever lanthanide ions doped with a different kind of host material, at that time, so radiative and non-radiative transition probabilities we can change. It will be changing from different kind of environment will be changes. At that time, automatically host material will be changes. Automatically lanthanide ions property will be changes. So that is why. So we can tune the radiative, non-radiative transition probabilities also, and our changing with the different host materials. That also one of the unique properties in the spectroscopy. These optical properties are important in estimating the lasing characteristics of any material. So this is the optical property are important in estimating the lasing characteristics of any material. Next, what is the main definition of glass? In term, glass is commonly used to mean the fusion products of inorganic material. So previously in olden days, the glass commonly used mean is the fusion product of inorganic material. which have been cooled to a rigid condition without crystallization. Without crystallization, whenever cooling to the glass material, that having the term previously used as a glass material. This definition would exclude splat quenching glasses made under high pressure, sol gel, and sputtering glasses. Different methods to to fabricate or synthesize the glass material. In 1968, glass was defined as an amorphous solid material which exhibits a glass transition temperature. So, glass material is nothing but a amorphous material. That means solid is amorphous material, and also non-crystalline material. We can say as a non-crystalline. Amorphous is nothing but a non-crystalline material, but it cannot show any crystalline peaks. Crystallization is you cannot see anything here. That is why glass is amorphous or non-crystalline materials. So glass transition exhibit more or less an abrupt change in the thermodynamic properties such as heat capacity, thermal expansivity, etc. These properties will be changed whenever the thermodynamic properties, whenever the glass transition exhibits. No, at that time we can changing or cooling. No, thermodynamic properties will be changed. That is such as heat capacity, thermal expansivity, etc. Next, chemically, glass is actually more like a liquid. Glass, we can see it will be like looks like a liquid type, but at room temperature, it is so viscous or sticky. It looks and feels like a solid. So, whenever solid material, if you are taking some chemicals, your boiling temperature will be increasing. At that time, in the melting temperature, at that time, it will be looks like a liquid and sticky type. After pouring the formation of the glass material, so that is look like a sticky. Next, so high viscous also. At high temperature, glass gradually becomes softer and looks like a liquid. So at high temperature, if more than 1000 degrees centigrade, we can heat the glass material. It looks like a liquid. It is the latter property which allows glass to be poured, blown, pressed, and molded into such variety of shapes. We can create a different kind of glass material. Shapes is given. We can circle, semicircle, square, rectangular. We can like optical fiber drawing also. We can draw the optical fiber also by using the glass material. So different kind of shapes we can draw the glass materials. Next, what is the importance of glasses? So glass is one of the most important material in modern information and communication and laser technologies. The drastical growing market for television screens and data displays need glass with a variety of coating on its surface. You are coating with some surface with a variety of coating. We can use the different kind of fluorescence glass materials we can develop. Glass is extremely stable against environmental attacks. Glasses are roughly speaking liquids that do not crystallize even at low temperature. If you decrease the temperature also, we cannot see any crystallization effect. So glasses are very versatile material due to the fact that they can be easily doped with transition metals or lanthanide or rare earth ions. So glass material is very useful or versatile material to easily develop the different kind of laser glasses doped with transition metal ions. Transition metal means manganese, chromium, iron, this kind of metals we can dope with different kind of laser glasses we can develop by using the transition metals. At the same time, lanthanide ions or rare earth ions doped with host material, we can develop the different kind of laser glasses. Next, what is the basic properties of the glasses? Glass is transparent but non-crystalline, a major paradox in the physics of condensed matter physics. Glass is electrically insulating at normal temperature. Glass is electrically insulating at normal temperature, but becomes conducting at elevated temperature, because at normal temperature it electrically insulated but it will be elevated temperature. That means we can increase the temperature or low temperature. At that time it becomes act as a conductor also. Glass usually breaks in a direction at right angles to the direction of maximum tensile stress. Glass is hard and yet brittle. When it cracks, it shatters at the speed of sound. Due to its brittle condition, there is no plastic deformation in glass, which will break suddenly when subject to stress exceeding its elastic limit. Whenever the elastic limit will exceed, at that time it can be break possible. So glass obeys Hooke's law. It's very, very important. Glass obeys the Hooke's law accurately until the stress is great enough to cause the fracture. If stress will be more pulled up means at that time only it will cause the fracture. Glass material will be break. So that is glass is amorphous material, at the same time non-crystalline materials. Whenever it obeys the Hooke's law, but until more stress will be built up means great enough, at that time it will be caused to fracture means break the glass material. So the coefficient of linear thermal expansion is almost constant for most types of glasses for temperature. So most of the glass temperature will be in the temperature range between the 400 degrees centigrade to 600 degrees centigrade. The actual value depends on the chemical composition of the glass. So the actual value, this is 400, 600 degrees centigrade, that is mainly for the telluride glasses or borate glasses temperature. So that is a most glass preparation temperature is 400 to 600. That is a example for the borate or telluride glasses. But the actual value depends on the chemical composition of the glass. So what you choosing of the chemical, selection of the chemical, choosing the chemical composition, constitution. No, at that time we can decide the what is the quenching or melting temperature of the glass material. So these are the very important basic properties of the glass materials. Next, what is the difference between crystalline and non-crystalline? Crystalline material and non-crystalline. Non-crystalline is nothing but amorphous material, that is solids. So in solids, on the basis of atomic arrangement, solids may be broadly classified into two categories. That is the crystalline and non-crystalline. So crystalline and non-crystalline means amorphous. Example is amorphous material is example is glass or plastic, these things. Crystalline material is example sodium chloride, NaCl, salt, that are also crystalline material. Diamond, crystalline materials. Next, graphite, crystalline material. These are the different kind of crystalline materials. In crystalline solids, both long range order and short range order exist in the arrangement of atoms. In the crystalline materials, atoms is arranged in uniformly, periodical arrangement. Sequentially, it will be arranged. That is why it's having the long range order and short range order in the crystalline materials. But in the case of amorphous or solid materials or glass materials, only short range order only exhibit. Okay, so that means here in the crystalline material, it exists both long range order and short range order. But in the case of amorphous material, that is non-crystalline materials, it exists only short range order only. In next figure shows the systemic representation of the order of crystalline form and random network amorphous for the same composition. These are shown in the next slide. Due to the short range periodicity, the atomic arrangement, the degree of disorder will be greater in an amorphous solid than its crystallization counterpart, and it will be having higher entropy compared to the crystalline phase. These are the glass material having the higher entropy compared to the crystalline phase. That is the difference between the crystalline and non-crystalline. That means crystal and glass material difference between the two materials, crystal and non-crystal. So this is the pictorial representation of the glass material and crystals. So molecular arrangement or atoms or molecular arrangement in the glass as well as crystal. First A, glass. Glass, see the structure here, see the, this is randomly arranged. It's not uniform. Uniform means if you see the crystal picture, each and every atoms in between the distance or space will be very uniform. Each and every atom in between the arrangements is molecular atoms or ions between the systematic arrangement. That is why crystal having the long range or short range order. Both will be belongs to the crystal. But in the case of glasses, this pattern is atom arrangements will be randomly arranged. It's not uniform. So yes, space will be less, sometimes more different shapes. So that is be randomly arranged. The pattern of the atoms arrangement will be randomly arranged in the glass material. But in the case of crystal material, atomic arrangements is the uniform, periodic. Each and every atoms in between the space and everything length will be interionic distance will be equal and same, uniform. That is why this crystal is having the long range order, but glass is having the short range order. That is why you can crystal, you are unable to break the crystal. You need to do some lasers. If you have to break the crystal means we need some different kind of lasers only we can use to break the crystal. But in the case of glass, we can easily break because it's having the short range order. But inside the solid material, atomic arrangements will be very, very short. That is why we can easily break the glass material. But in the case of crystal material, each and every atoms arrangement will be very periodic and uniform. It's a long range order. That is why we can unable to break the crystals. That is why if you want to break the crystal, we need different kind of lasers. Then only you can break the crystal. But in the case of glass, we can easily break. That is the main thing is this atoms arrangement is random. At the same time, short range order. This is long range order. These are the main difference between the molecular arrangement difference between the glass and crystals. Next, glass materials have advantages over crystals in many optical device applications. The advantage includes flexibility of choosing glass composition over a wide range. We can use very wide range or flexibility choosing the glass compositions. That is one of the important advantage of the glass materials. Next, a disorder ion environment that can broaden fluorescence bandwidth. We can tune the fluorescence bandwidth by using the different kind of host materials. We can choose the different kind of fluorescence bandwidth. Next, uniform isotropic optical properties over a wide range of composition. Different kind of composition, we can change the optical properties over a wide range of composition. Next, easy of fabrication into complex shapes including fibers. We can easily fabricate by using the different kind of glasses including shapes of the fiber also. Shapes including fibers also. We can draw the fiber also by using the glass material. There is fibers manufacturing is a little bit difficult, but easy of fabrication in glass material is very easy, economically cheap also. So low fabrication cost. Glass material we can synthesize or fabricate by the economically cheap, low fabrication cost, which leads itself to mass production. We can produce high mass of the glass material also. We can develop by using the glass materials. The possibility of producing a large active stress with good optical quality. This is very optical quality of good laser glasses also. We can synthesize or fabricate by using the different kind of lanthanide ions. Doped with the lanthanide ions, we can fabricate the different kind of high quality of optical laser glasses. These are the important applications in the glass material. Next, these are the different references in today talk which discussed. These are the cited references are total 8 references. Each and every reference is cited in our lecture. These are the references of the today talk. So, thank you.
Like, share and subscribe. Hit the bell icon for more updates.